Earlier on we derived the critical angle equation, but the key thing is, well, what's the point of it? What actually happens? Where do we get use from it? Well, we need to understand what happens when our angle of incidence is less than critical angle, what happens when it's equal to it, and what happens when it's greater than it. So if you have an angle of incidence that is smaller than your critical angle, you will get refraction. So this happens when theta incident is smaller than theta critical. If you get to a situation where you are on the critical angle, so theta incidence equals critical angle, then that's when we get our angle of refraction of 90 degrees, and we see refracted rate is going along the boundary. The third situation, if we are exceeding our critical angle, is we now got our refracted ray not on the opposite side, but is now reflected back into the original material. And this, so theta I is greater than theta critical, and this is called total internal reflection. And we get that when our incident angle has exceeded the critical angle. The main place we see this is in fibre optics. So fibre optics are a really good use of this total internal reflection. It's something that they love asking about in exams. So you've got your fibre optic cable, and in the core you have your light ray undergoing total internal reflection along, so that the signal is passed from one end to the other. With fibre optics, there are two key things that have to happen. The first thing is they have to be narrow. If we have a very wide fibre optic, then the path length of this totally internally reflected ray is going to be considerably greater than one that just passes straight through. What that means, if we've got a significant difference in path difference, is the time taken for the ray to reach one end to the other is going to be significantly greater, so that our ray is going to be spread out. That means the signals have to be sent at larger distances, so our rate of transfer is reduced significantly. So by having a narrow fibre optic, what that means is the time each individual signal takes can be reduced, so we can get a lot more data sent through. The other key thing we have to have is cladding. So cladding is essentially another layer of material on the outside of our fibre optic core. This material and cladding must be smaller than end core. The reason for that is we need to have total internal reflection happening at this boundary here. If end cladding was greater than end core, we wouldn't get that total internal reflection. And the reason we have this is to stop leakage. The reason it stops leakage isn't actually as straightforward as it seems, because theoretically they should have a very similar performance whether you have cladding or whether you don't have the cladding. But the reason we have it is because we live in an imperfect world, and we don't have situations that mirror lab conditions. So we've got our two fibre optic cables, one with the cladding, one without. And we're going to have some contamination on the outside of our fibre optic. And this is going to be grease, and the refractive index of this grease is going to be greater than the core. What that means, when our light ray comes in and reaches this point here, we're no longer able to get total internal reflection. That means our light ray there is going to be transmitted out of the core and therefore leaked. In the example with the cladding, this boundary hasn't been compromised, so we will still get the total internal reflection along the fibre optic. So that's why we have cladding. It's to stop leakage when we have contamination around our fibre optic.